Chapter 21 is the study of nucleophilic acyl substitution. Now, in its generic form, this is taking advantage of a leaving group attached to a carbonyl. So it's at least superficially similar to what we saw for the SN2 reaction, where we bring in a nucleophile and a leaving group leaves. That's at first glance. Reality is that we're still taking advantage of the carbonyl functional group. So as for what we saw with the aldehydes and ketones, nucleophilic attack is not going to just attack the carbon and displace a leaving group. It actually has to involve the carbonyl. So we've done this to death already, but let's do it again. Nucleophile attacks the carbonyl group, breaks the carbonyl pi bond. That gives us this as a tetrahedral intermediate. At this point, we change directions from what we saw for aldehydes and ketones, because at this point we actually have the possibility of reforming the carbonyl. If we use the lone pair on the oxygen, the anion, the negative charge, to come back in, reform the carbonyl, we would end up displacing either the nucleophile or the X group, leaving group. Now, of course, the whole point is we don't want to go backwards, we want to go forwards, so we're going to end up using that X group, whatever it happens to be, as a leaving group, hence the word substitution. So overall, it looks a little bit like the SN2 reaction. It is not. There's a lot more going on here. Make sure you know what it is. On to what we call those leaving groups. Now, there are a couple of different derivatives, all of which are derived from carboxylic acids. So we sometimes just refer to them generically as the acid derivatives, which we're going to talk about in this chapter. Now, your book discusses some of them in more detail than I will, so be it. They are in order of reactivity. First, the acid chloride. This is the most reactive of the lot, and as such is the most versatile of the whole lot. Problem there is that being too reactive can sometimes get you in trouble. So we will have some issues in handling that. We'll talk about that a little later. Next, the acid anhydride. Your book talks about this one in some detail. I'm not going to spend a lot of time on it because, to be honest, it's very hard to make, and it's just easier most of the time to go through the more reactive and easier to make acid chloride. The reactions are similar up to a point, so if you know one, you sort of know the other. The ester. Now, this is the first of the stable derivatives. Both the acid chloride and the acid anhydride react with things like water very readily. The ester does not. Esters are commonly found in a number of different places, but some of the ones that we use commonly are perfumes and artificial scents, are typically esters. And lastly, the amide, the last and least reactive of the lot, the most stable of the four acid derivatives that we're going to talk about. Now, this one is not susceptible to virtually any of the reactions of the other three, which is a bad thing for an organic chemist trying to make new compounds, but it's a very good thing biologically. Now, this is the type of bond that exists between the individual amino acids in your proteins, and so you really wouldn't want that just falling apart every time it got near water. It might cause some problems. So this one will not have a lot of reactions involved with it, but the ability to make it is a very important one. Okay, now let's talk about the acid chlorides. If we're going to talk about using these, we have to be able to make them, and it has to be a pretty direct process. We don't want to spend a lot of effort in sidestepping so that we can make a functional group and then just turn it into something else. It has to be pretty easy to make that intermediate group, otherwise it's not worth the effort. Well, the acid chlorides actually follow what we saw for alcohols back when we talked about the SN1 and SN2 reaction, and that is that we can take a carboxylic acid, treat it with thionyl chloride, SOCl2, and replace the OH group with a chlorine. Now, as I said, the substitution reactions that we see for carboxylic acids and their derivatives are not identical to those that we saw for the SN1 and SN2. We will always involve the carbonyl, so don't oversimplify the way that this works. But in the net, what happens is exactly the same. We replace OH with Cl, and we have some leftovers. Sulfur dioxide, which leaves as a gas, and hydrochloric acid, which will mop up some other way, or we'll let it evaporate as well. How does this work? Well, we begin with using the most nucleophilic of the two oxygens to attack the sulfur. Now, this is parallel to what we're seeing For carbonyl groups, we're using it with a sulfonyl group. So we're attacking an S double bond O very similarly to what we would do for a C double bond O. Now, when we do that, we get a variant of the carbonyl tetrahedral intermediate. It's a sulfonyl tetrahedral intermediate, but the same principle applies. The lone pair on the oxygen can come back in, reform the second bond to sulfur, displacing a leaving group, in this case, one of the chlorines. Now you notice that still doesn't leave us with a neutral compound. We still have a charged intermediate here. I still have a cation on oxygen. What I need to do is neutralize this, as soon as possible. So we can envision this as the chlorine coming back in, taking off the acid proton, and then resonating that into the oxygen pi bond. That would neutralize the charge for the entire structure and give us this sulfonate ester, sort of mixed ester. Okay, well, we still haven't figured out how we're going to get to where we need to be. We still have chlorides around. HCl that formed in the previous step is virtually completely ionized, so we still have a nucleophilic chlorine we can work with. So if we use that as a nucleophile and attack the carbonyl, we break the pi bond, we get to the tetrahedral intermediate again, like so. Now in this case, as I said before, carbonyl chemistry, as far as the acid derivatives, takes advantage of the fact that we can reform the carbon to oxygen pi bond. So we do that, we displace a leaving group. In this case, it's easier to displace the SO2. Why? Because it's a gas. We don't have any reversal possible. So even if the equilibrium was heavily against forming the chloride, eventually we'll drive towards forming the acid chloride because the SO2 floats up and out of the reaction. So there's no equilibrium possible at that point. So as a result, the byproducts, sulfur dioxide and formerly hydrochloric acid, although it's going to be just H plus in solution with the chloride ion being used as a nucleophile later on. It's a relatively clean reaction, and it works for virtually any type of carboxylic acid, no matter what the R group happens to be. It's a very versatile reaction, and because the acid chloride is the most useful of the carboxylic acid derivatives, it's very handy to be able to access it easily. Alright, now having said that, so we can make an acid chloride. Yippee skippy. We have to be able to do something with it. As it turns out, because it's very reactive, we can do quite a lot with it. We can replace that chloride with any number of nucleophiles, and they don't even have to be all that strong of a nucleophile for this to work. It works, as I had mentioned before, the nucleophile coming in. Instead of displacing the chlorine, however, it actually breaks the pi bond to oxygen instead. So this is where we differ from the SN2 reaction. But the next step, that broken pi bond is reformed. And in reforming, the chloride is actually displaced. So we end up with, formally overall, a nucleophilic substitution. But it's more along the lines of what we saw for electrophilic aromatic substitution, where there are multiple steps involved. In this case, we have nucleophilic addition followed by elimination. The net is a substitution. Now, just a couple of the nucleophiles we could manage here. The first one, water. If we treat an acid chloride with water, we get to a carboxylic acid rather quickly. Now, having grown up in the southeastern United States, this is a real problem because the water that we're worried about here is humidity. The atmosphere there gets relatively humid, especially around summertime. Right about now, the humidity has actually passed the temperature, and we're still in the 90s in the south. So we have some issues here. One of the things we don't talk about a lot in the lecture course is what really are the issues in the laboratory portion. In this case, there's a real handling issue here. We're creating something that by its very nature is unstable and reacts with moisture. Well, we have to work to keep that away. Since we make acid chlorides directly from the acid, this is not a nucleophile you would generally use intentionally. This is bad technique. Wet glassware or a humid atmosphere that you didn't put a drying tube on top of the reaction, and you end up with a carboxylic acid and wonder how you got there. A very similar reaction that we do use a lot, however, is rather than using water as our nucleophile, we use an alcohol. Now this gets us two esters, and as I mentioned in the intro, Esters are used as artificial scents for a great many things, so it's very useful for us to be able to make them directly. So this is one case where we can manage that. It follows the same paths that we see above. We can also access amides the same way. If you use an amine as the nucleophile, we end up forming an amide. Now, with some things that we saw for the aldehydes and ketones, they still work here. I can use something like lithium aluminum hydride. In the case of a ketone that gave me a secondary alcohol, well, here I'm looking at getting a primary alcohol out of this because I end up adding 2 hydrides, so that I end up with 2 new hydrogens on the carbon. The first nucleophilic attack, if you put an H where I have if you put an H where I have nucleophile written above, you'll see you end up forming an aldehyde. Well, the aldehyde actually is more reactive than the ester, or than the acid chloride was, and so it will get hit by a second nucleophile very quickly and give you the primary alcohol. The same trick works with Grignard reagents and, alkyl lithium reagents. As your nucleophilic carbons come in, the first one will actually give you a ketone, and then it will get hit again very quickly. So you can actually put 2 identical groups around an alcohol by starting with one of the acid derivatives and using a carbon nucleophile. Okay, now let's take a look at the esters. First, as before, we have to be able to make them. We can make them from the acid chloride. That requires some amount of handling skill, and sometimes it's a little bit unpleasant, particularly if you don't have good ventilation. That reaction can really hurt. Trust me from experience on that one. One way that we can make esters, provided we don't have anything particularly acid sensitive in the molecule, is to treat the carboxylic acid with the alcohol and a strong protic acid. Now, this is called the Fischer esterification. It's named after Emil Fischer. It's a very old reaction, but it's one that actually works very well with a variety of structures, and it's generally less costly and less difficult experimentally than dealing with acid chlorides because it's not so sensitive to conditions. So how does it work? Well, we've pretty much established by now that when you put sulfuric acid in place, it's the serial protonator. It's going to protonate everything in sight. Does the same here. It will actually protonate a carboxylic acid. At that point, much as we saw for the aldehydes and ketones, we have a very weakened carbon-2-oxygen pi bond. So if we bring an alcohol in as a nucleophile, this sort of approximates what we saw for SN1 reactions of alcohols, where we can actually bring in a very weak nucleophile and still get the job done. We use water then to neutralize the structure, and we're back at a tetrahedral intermediate like this. Well, I don't have a good leaving group here. Now, before when we did the acid chloride, we had a very obvious leaving group. I don't have that here. So what I'm going to have to do is create one. And the way that I do that from alcohols, OH groups, is I protonate them again. So another molecule of sulfuric acid is used to protonate one of the 2 OH groups. Now I do have a leaving group. And I can displace it internally. And so that is generally what's thought to happen. We have the pi bond forming an internal displacement of water. At that point, we have the protonated version of an ester. And all it takes is water or another suitable base to remove that last proton, and we found our ester. And so we haven't gone through anything more reactive than the acid. We haven't gone anything that's potentially reactive with water, although that will be a problem for us sometimes with this reaction. But we have managed to make an ester very directly, and it works great. All right, now let's quickly look at some of the nucleophilic additions that we can do to esters. Now, the mechanism for this is virtually identical to what we saw for the acid chloride, involving direct nucleophilic attack on the carbonyl, and then reformation of the carbonyl with displacement of the ester alkoxide group. But the alkoxide is not nearly as good of a leaving group as the chloride was. So we're going to have a diminished reactivity here, which will limit what we can do. First and foremost, breaking off the ester group to reform the carboxylic acid, or to form the carboxylic acid, is not trivial. With an acid chloride, we could just treat it with water, and the reaction proceeds extremely rapidly, almost violently in certain cases. In this case, there's not a favorable leaving group to begin with, so we have to aid things along, either by protonation to aid in displacing the leaving group, or we have to pump up the strength of the nucleophile by using something like hydroxide. We'll talk about those individually in a little bit later because we need to talk about those in detail. We can do a process known as transesterification, that is, forming one ester from another one, by just using a different alkoxide as a nucleophile. And of course, here we would want to use statistics, as that's really the only driving force that's going to get us past this. So we would use a large number of equivalents of this alkoxide so that we didn't have to compete with the original ester leaving group. We can make amides by a similar process, only the amine is a strong enough nucleophile where we don't really require it to be deprotonated to get this job done. So we can do that by direct nucleophilic displacement to form amides. And as before, we can also still use the hydrides via the aldehyde to get to a primary alcohol, or we can use Grignard reagents, which will take us through an intermediate ketone to get to a tertiary alcohol. These are still viable, and those mechanisms we've done in detail in the past, so we're not going to cover those again here. Okay, now, the ester is sometimes used not just as a perfume or other scent, but it's used as a protecting group for carboxylic acids. So one of the things we have to be able to do with them is to be able to get the ester back to the carboxylic acid, break the ester bond. And we can go about that in one of two ways. We can go about it under acidic conditions, which we'll just call ester cleavage, or we can go about it under basic conditions, which is called saponification. And oddly enough, it's called that because it actually is a process used to make soap, and that's how old it is. It's a very, very old and traditional chemistry, understood well before the actual ester bond was really well understood. So let's first look at the acid version. It's very, very similar to what we saw for the Fischer esterification, just in reverse, where we're using water as a nucleophile now instead of the alcohol, and the hydronium ion to protonate things instead of sulfuric acid. So you might want to write these two down side by side and compare them, and you'll see they're almost identical. So let's look at it. First, the ester, if we put that in place with the hydronium ion, we'll get protonated very quickly. Again, as before, we have a weaker carbon-to-oxygen pi bond now, so it's susceptible to attack by weaker nucleophiles, even water. So here's water coming to do the job, breaks the carbon-to-oxygen pi bond. Once we neutralize that, we end up with the tetrahedral intermediate, the same tetrahedral intermediate that we had for the Fischer esterification. Now at this point, we're interested in getting rid of the OR group. We're going to have loaded the statistics here by putting a lot of aqueous acid in place. So despite the fact that it is in equilibrium with the ester, we're going to win with sheer numbers. So protonation of the alkoxide group by another molecule of the hydronium ion gives us now a leaving group similar to what we used water for in the Fischer esterification. Internal displacement, just as before, gives us the carboxylic acid in its protonated form, and then a final neutralization of that with any suitable base, most likely to be another molecule of water. And we managed to get all the way to the carboxylic acid. Now, this is useful for us because, as I said, we will sometimes have to use esters as a protecting group for a carboxylic acid. When the OH, the acidic hydrogen, is our problem, we can put it out of the way for a little while and then regenerate it whenever we want. Okay, last but not least, let's look at what we can do with the amides. It's a really short list. The amides are exceedingly stable, so displacing them with any common nucleophiles in the way that we can do with the chloride of an acid chloride or with the alkoxide of an ester is virtually impossible. Amides don't typically react with Grignard reagents. They will react with lithium aluminum hydride, but only under extreme conditions, and not to give an alcohol, but instead to give an amine. We'll talk about that reaction in the amine chapter in more detail, but you can look at a brief summary of it on page 797. The only real reaction that we need to worry about for amides is the ability to hydrolyze them back to the carboxylic acid. And even that requires conditions that are fairly brutal. We're talking about either very strong protic acid or very strong hydroxide solutions and a long period of time. So, for all practical purposes, the amide functional group is a dead end. We form it, and then we are, in the absence of extreme conditions, pretty much stuck with it. Now, as a chemist, that'd be a little bit frustrating. As a person who relies on those amide bonds between proteins, well, I'll tolerate the fact that they're stable. I sort of like being alive. I'm assuming you do too.